All right, let's do our first example of rotational kinematics with probably one of the most frustrating experiences that we all experience at some point. Have you ever noticed that whenever you are, loading up butter onto bread and you accidentally drop it, it always falls butter side down? Or when you load it up with jam and you accidentally drop it, it always falls jam side down? I don't understand it. It's really weird. But let's make a physics problem out of it, okay? So imagine you have the situation where you loaded it with butter and you want to find out what must be the smallest rotational speed that this bread must fall and the greatest rotational speed that this bread must fall in order for it to fall butter side down, okay? And to be clear, this bread, this will be my bread, this will be the butter, right, is falling a distance of 56 centimeters, so 0.56 meters. Okay, and we want it to fall butter side down. Now, the first thing to ask is, what are the conditions such that this bread is going to fall butter side down? Well, here's the thing. If it, if this is the butter side, right, this is the butter side, and it falls and rotates pi over 2 radians, in other words, a quarter of a full revolution, it needs to rotate a minimum of that amount in order to fall butter side down, right? Because it'll fall here and then just collapse this way, right? And the maximum amount it can rotate is basically 3/4 of a revolution, because then it can still bounce back this way to be down, okay? So here's the thing. The minimum, the theta minimum, right, would have to be pi over 2, and the theta maximum would have to be 3 pi over 2, right? So in order for it to land butter side down, it has to rotate a minimum of pi over 2 or a maximum of 3 pi over 2. All right, now let's bring in our kinematic equations, right? We have the famous kinematic equation that theta equals omega 1 t plus 1/2 alpha t squared, right? But notice in this problem, I'm not talking about acceleration, right? This is just released and it's set to go, and there's some initial omega, but this problem does not talk about any kind of angular acceleration, right? So this is just this is the linear equivalent of if you're just running at a constant speed, okay? Which means if that alpha is 0, this guy can just go away, right? So basically then there's 2 options. There's going to be a theta min, right, and an omega min, right, that's associated with the minimum speed required to get it to land butter side down, right? And then there'll be a second guy, which is theta max equals omega max t, okay? Now, we already know that the minimum theta is pi over 2, right, which equals omega min t. But we have this other issue, right? We don't know time yet in order to calculate our minimum omega or angular speed required to get this guy to land butter down, all right? But we do know from, just our basic linear kinematics, how long it would take to get this to fall if it falls from a certain height. And you guys probably will remember, I'm going to put it up here, d equals 1/2 at squared. I didn't put the v0t because we know that it starts from rest, right? But we know that this is 0.56, right? And that's 1/2, and this is 9.8, which means the amount of time that it takes for it to fall, if I solve this equation, and you guys can check me, is 0.34 seconds. Cool. 0.34 seconds. It takes 0.34 seconds for this to fall, which just means that our minimum angular speed for the toast to land butter down is pi over 2 divided by 0.34, okay? And I get a value of, what do I get? 4.6. So I'm just going to bring it up here. Omega min is going to be 4.6 radians per second. So as long as this toast falls and rotates at 4.6 radians every second, it will be at the minimum speed required for it to land face down. Okay? And for the maximum, I want to do the same thing, except, my theta max is 3 pi over 2. Right? So my omega max is going to be that 3 pi over 2, once again, divided by how long it takes it to fall, which is 0.34 seconds. Right? So my omega max, right, the maximum angular velocity that this thing can turn so that it goes almost 3/4 of the way and then falls back down, butter side down, is going to be, I get a value of 13.8 radians per second. Cool? So if this butter turns any slower than this, it's not going to land butter side down. And if it rotates any faster than this, it's not going to rotate butter side, or it's not going to fall butter side down, right? So next time, you are doing your little, breakfast fixing, just make sure you don't drop it at between these speeds, and you're going to be fine. Okay? It's a public service announcement.